am so happy you joined me as we delve into a better understanding of ionic bonding. Now, in ionic bonds, what we are looking at is the exchange of electrons or the transfer of electrons from an atom of low to an atom of high electronegativity. Metal atoms tend to donate electrons. When they give away electrons, they become less negative. So if you think of it as less negative and more negative, that can be really helpful because electrons are negative particles. So if it's less negative, it becomes a cation. C, a positive ion. The process is called oxidation. The nonmetal, conversely, tends to accept electrons to become an anion, a negative ion. Do you see how the words kind of imply? See, a positive, that T looks like a positive sign, ion, a negative ion, and we say that it is reduced. Now, typically, questions are going to ask you to predict bonding based on a classification of the element. And so cations would be metal ions with a non-metal anion, a metal cation with a polyatomic anion, ammonium, hopefully you know your polyatomic ions, or I tell my kids they're in big trouble. Okay, so ammonium is positive with a non-metal anion, or ammonium with a polyatomic ion. Now, typically, a bond will exhibit more than 50% ionic character if the difference in electronegativity is greater than or equal to 1.7. You'll see slightly different numbers, maybe 1.6, 1.8 in different textbooks, but 1.7 is a nice round number that is commonly used. So let's take a look at substances that we would typically predict would be ionic. We would name them ionic. We always name based on predictions. But let's see. So we have a bond here between sodium and chloride. The electronegativity of sodium is 0.9. For chlorine, it's 3.0. You don't have to do this unless you're given electronegativity values because it's not something you memorize. So in this case, my difference in electronegativity is equal to 2.1. Sodium chloride is kind of your penultimate ionic compound. Let's look at beryllium iodide, where we evaluate one bond, not the whole molecule, just a bond within the molecule. Beryllium is 1.5. It's a metal. Iodine's a non-metal, 2.5. We would think that this would be an ionic bond, and lo and behold, that difference in electronegativity is 1.0. Not so ionic after all. Let's look at aluminum. So we have 3 bonds between aluminum and bromine. You only do a bond. We don't multiply this by factors because there are 3 bonds. We have 1.5 and 2.8, metal, non-metal, predict it to be ionic. Lo and behold, its difference is 1.3. And so it doesn't even have 50% ionic character. Copper to chloride. Copper is 1.9. Chloride is 3.0. My difference is 1.1. So again, we classify. Typically, you're going to go based on your classifications, but this gives you an idea of how you can actually use electronegativity to calculate it. Now, general structure. Crystal structures of ionic compounds is very complicated. I don't go into them at the AP or IB, or even when I taught college. I rarely had time for this. But what we have is an ionic structure. It's an alternating positive and negative in a rigid lattice. kind of like those latticed fences that you will see. Electrons are transferred, not shared. Okay, and we call it a formula unit. I typically say it's the only time you can say F you to your teacher and not get in trouble, because we're talking about formula units, of course. Okay, now these are fixed into place, and we have a long-range network of alternating positives and negatives. Because positives repel positives, negatives repel negatives, they need to alternate to minimize that repulsion. And we always have a present in a simplest, we always reduce it to the simplest whole number ratio. So calcium chloride's always 2 chlorides to 1 calcium ion. And that's how we define their formula units. Now, let's take a look at some of the common oxidation numbers of our representative elements. Those would be those in the S block and the P block. So groups 1 and 2 and then 13 to 18 are our representative elements. Group 1, if it's a pure substance all by itself, its oxidation number, its ionic charge is 0. Okay, nothing to give electrons to, nothing to take electrons from. So group 1 always loses an electron. So when there's a loss of 1 electron, it becomes +1. Group 2 has a loss of 2 electrons. Group 13, I actually like to memorize this a little bit differently, but the metals are going to be a loss of 3 electrons. Okay? Non-metals gain. So when you get to group 14, you have both non-metals and metals. The non-metals can gain 4 electrons. The metals can either lose 2 to become +2 or 4 to become +4. So we're always dealing with our outer S and P valence electrons. And so they can lose, they usually, they have 2 S's and 2 P's. They can lose their P's to become +2 and their S's and P's to become +4. So nonmetals in group 15 become -3. Metals can be +3 when they lose their P3s, or +5 when they lose the S2 and P3 electrons. Group 16 gains 2 electrons to become an ion. Group 17 gains 1 electron. And the goal here is to have that stable octet of electrons. Not everything reaches that octet, but that is a goal. So let's take a look at another group that have firm oxidation numbers. I like to call them the silver steps. Okay, I'll fill that blank in just a minute. So if you find silver for the silver steps, that's my first step. It's either pure silver all by itself, in which case it's 0, or it's +1. Then we go cadmium and zinc, 2 elements +2. Aluminum, gallium, and indium, 3 elements +3. 0, there's 0 when they're all by themselves. Okay, but +1, one step is +1, 2 and +2, and 3 and +3. So I ask my students a lot, is it group 1, group 2, or the silver steps? If that answer is yes, then they have firm cation charges. Okay, so let's see how this looks on the periodic table. A lot of students like to label their periodic tables. So remember, pure elements are 0, but what we want to look at here is I'm going to be labeling ionic charges. Oxidation is bigger than ionic charges, but ionic charges are a subset you can think of oxidation. So group 1 would become +1, group 2 would become +2. Okay, the noble gases would be 0. The nonmetals would be -1, -2, -3, -4. Okay, and then we have our silver steps. 1 step for +1, 2 at +2, 3 at +3. So +1, +2, +3. Okay. Now, these transition metals, they do wild and crazy things. And so we'll have to be told somehow in the context of the question, either by determining it from the formula or being given Roman numerals in the name to tell us what the charge is when there are multiple charges. But you would not see a Roman numeral if it was group 1, group 2, or part of the silver steps, because those have firm numbers. Any chemist knows what they are, so we wouldn't bother saying it with a Roman numeral. Okay, thanks lots for joining me. Have a good night.